Example 4, the standard graph of an exponential function, where we have like b to the x. In this case, we just have a 1 in front of whatever's going on. If b is greater than 1, here's what's going to happen. This is exponential growth.
Exponential growth. And here's how fast exponential growth grows. For example, if you start with 1 foot off the ground on the x-axis, just like you're making this mark right here, okay?
Yeah.
1 foot off the ground straight up. And let's say we have just a base of 2. So let's just say we're graphing 2 to the x.
Okay.
By the time you move 24 feet away from where you started,
Yeah.
your altitude would be in the vicinity
Yeah.
of the moon. That's how fast exponential growth grows.
That's pretty crazy.
No lie.
So to the right, this graph is going to start going up at a reasonable-ish rate and then just
like a
shoot
rocket
up.
shoot into space.
And then to the left, what happens is it gets closer and closer and closer. This is actually kind of a terrible graph.
But it never hits zero, but it
hits
gets really
zero.
close, yes.
So this is, and this could end up being, like he said, this could end up being like 2 to the x. We could be talking about 3 to the x.
We could be talking about e to the x.
E to the x, because we're about to start logarithms, so e's are going to start showing up. So, or if we really want to get crazy, we could do pi to the x.
Slow down that craziness. Whoa.
But this that we're about to do, this analyzation, it should be really similar for all of these things that have some number bigger than 1 to the x power. So domain, we can plug anything we want in.
Anything we want to.
So all reals.
All reals. Negative infinity, positive infinity, all reals, capital R, whatever.
Not all reats, which is what I initially wrote. Sorry. Range is...
Now you have to pay attention here because you're either going to be above or below the x-axis.
Right.
So that tells us where our range is going to be.
Yeah, because we aren't actually going to ever get to 0. We're just going to get close to it. So we'd need parentheses 0 since it's not ever going to equal 0.
Right.
And then it goes up forever.
Forever
until it gets
and
to
ever.
Infinity.
Yes.
Continuity. This is continuous because
Totally
you can draw
continuous.
it without picking up your pencil.
Right. Continuity.
Okay, the symmetry.
There's no symmetry here because it's out of whack.
Is this bounded?
It is totally bounded below because it never falls below the x-axis.
Right.
Or if this graph were to move up or down, it hits that floor and it just doesn't go through the floor.
That it's not going through.
Yeah.
Extrema.
No extrema on this. Extrema would indicate that we have peaks or valleys or mountaintops or whatever
you want to call it. Basically a point where we're going from increasing to decreasing.
And that is not happening here.
Which, by the way, that's not listed here, but is it increasing or decreasing?
It increases from negative infinity to positive infinity. It does not ever decrease.
Yeah, and that's part of why there's no extrema, because extrema happens when you go from increasing to decreasing.
Yes.
Asymptotes.
There is an asymptote at y equals 0 because it puts that infinite, when you look at negative infinity, there is a limit there of 0, which indicates a horizontal asymptote.
That's right. So in behavior
would be infinity because
the in behavior as x is going to negative infinity, right? Is that's the one we want, right?
Right there.
Or do we want both ways?
Well, if you go towards negative infinity, that's your horizontal asymptote. So which would be 0. So I think in this case, our in behavior, it's okay to look at the side that's going up.
Okay, so when we go towards negative infinity, it's going towards 0. When we go towards positive infinity for x, we're going towards positive infinity.
Yeah, that's it. That's how it goes. And so the decay function is almost this exact same thing, but in flippies.
Yeah, so our initial value here is 1 again, but this time we're going to get closer and closer to 0 this direction.
Right.
And we're going to go up and up and up, go in this direction.
And way up.
So in this case, because b has to be less than 0, we could be graphing things like 1/3 to the x.
Right.
So here's what they'll do sometimes, by the way. Instead of writing 1/3 to the x, they could tell you that this is 3 to the negative x.
That's the same thing. They could. Or they may even say 1/3 to the x, which looks a little bit weird, but again, it's the same situation.
Yes, because if we rewrote 3 to the negative x or 1/3 to the x, we could rewrite it in this in this way that shows that b is actually less than 1.
Right, right.
So the domain, again, is all reals.
It's all reals. We can put whatever number we want to into the exponent area.
Yeah. Our range is still 0 to infinity.
Yes. Because we're above the x-axis. We're still continuous. We still have no symmetry. So all of that is the same.
And we're still bounded.
We're still
the same
bounded
way.
below because, again, we don't fall below the x-axis. We still have no extrema because there's no place where our function increases and then changes to decreases and then changes to increasing again.
But what about, where is this increasing or decreasing?
Well, now, as you move from left to right, what is the value of y doing? So as you start on the left and you move to the right, it is decreasing the whole entire time.
Okay, and so...
The asymptote, again, would be y equals 0 because the limit... Now, this is where we look at the limit going towards positive infinity. The limit towards positive infinity is going to be 0. Okay? The limit towards negative infinity will be more of our in behavior situation. But this limit right here would be 0. Or no, this
so
limit right here would be
infinity
positive
would be
infinity.
And then the other one
Right.
is 0.
0.
So that's analyzing some exponential functions for you.
Yeah. Yar.